Why is sigmoid activation not preferred? In the last lecture, we learned about sigmoid activation function. What did we learn? We learned what is sigmoid activation function, how to use it, what is the formula for it. We also learned about the derivative of sigmoid and how it is useful. We also saw the use cases of sigmoid. In this lecture, what we want to do is we want to understand why is sigmoid not the preferred activation function. When I say it is not the preferred activation function, I do not mean to say that you don't use it anywhere. Mainly in the hidden layer of your neural network, you generally don't use a sigmoid activation. In this lecture, we are going to learn why logically and why mathematically this is not the right option. Okay? Now let us understand this in detail. First thing you want to know, whatever we learned in the last lecture, from that, what is the formula for sigmoid? Sigmoid of x, it can be found as 1 by 1 plus e raised to minus x. This is the formula for sigmoid. And what did we learn about the derivative? We learned that derivative sigma dash of x can be found as, this we learned can be expressed in terms of sigmoid itself. That is sigmoid of x into 1 minus sigmoid of x. This is how you can express the derivative of sigmoid. And this is a very big positive for sigmoid. That is, if you have sigmoid as the activation function in any particular layer, you can use the sigmoid value that you calculated during forward propagation in order to calculate derivative during backward propagation. That is the advantage that you get. You don't have to calculate it twice. Instead, whatever values of sigmoid you calculated during forward propagation, you can make use of that in order to find out the derivative while doing backward propagation. Okay, this was a very big positive for sigmoid. Now let us see what happens when you use it in activation layer and what is the negative side. Okay, first thing you want to understand here is what values it will take. You know it will take values 0 to 1, but under what circumstances? First thing is, let us say the value of x, if this is a very large positive number, then what happens? In this particular case, the value of sigmoid of x will be very close to 1. This is the value it will take. And what about the other case? What if your x is a very large negative number? In this case, what happens? You know sigmoid of x will take somewhere near to 0. So something very close to 0. Next point is very important. Coming to this activation function, you should understand what values derivative is going to take. I am stressing on this because in this particular lecture, this point of what values derivative will take, this is very important. Let us see what value derivative is going to take. Sigma dash of x. Think about this from this formula. What is the maximum possible value that the derivative can take? If you think it happens when sigmoid equal to 1, then the problem is, if you use this formula, 1 into 1 minus 1 will be 0, which means this surely is not the greatest value. What if sigmoid is 0? Then it will be 0 into 1 minus 0, which will also be 0. That means the derivative takes the largest value somewhere else, not at sigmoid equal to 1, not at sigmoid equal to 0. Instead, if you look at this carefully and analyze, you will understand that it will take the largest value when sigmoid is equal to 0.5. That is, when it takes the value right in the middle of its range, that is when the derivative sigma dash of x, that will take the maximum value. And what is this maximum value? If sigmoid is 0.5, then sigma dash will be 0.5 into 0.5. What is this value? It will be 0.25. This is an important point for this particular lecture. Maximum value sigma derivative of sigmoid can take is 0.25, which also means the value of derivative will always stay between 0 and 0.25. Okay, keep this in mind. That is, Even though sigmoid takes values between 0 and 1, the derivative always takes value between 0 and 0.25. Okay. Now it's time for us to understand each of the negatives. First problem. First problem with sigmoid activation is something called as vanishing gradients problem. What is the problem here? If you see, the value of sigmoid is between 0 and 1. We also understood that the gradient takes value between 0 and 0.25. Here the main problem is value of sigmoid is a decimal lesser than 1. Whenever you have something lesser than 1, 0.7, 0.6, anything like that, then when you multiply two such values, the resultant will be having a lower value. It will be lower than 0.6. It will be lower than 0.7. So this problem, not necessarily lower than both the values, but surely lower than the larger value, and most of the times it is a lower value than you will expect. That is, generally if you expect to multiply two numbers, they will go higher. But when you take two numbers which are lesser than 1 and you multiply them, they will always come down. This is the problem here. Because of this, what happens is, whenever your sigmoid value is very large, or if it is very low, very large means something near to 1, very low means something near to 0. In both these cases, your derivative sigma dash will always take a value very near to 0. Even if it is near to 1 or if it is near to 0, your derivative will always take a value which is very close to 0. What is the problem now? When your derivative is very close to 0, now think about this. Where are you going to use this derivative? Let us say you have a neural network. Then where will you use the derivative? You are using the derivative during backpropagation. So if these are the layers in your neural network and you want to make use of derivative in the backpropagation, now think what happens. How do you calculate contribution of each neuron to loss? Okay, so let us say you found some loss or error. There is some neuron here. You want to find out the contribution of this neuron towards your loss. Then only you can update the value in this neuron. If you want to update the value of parameters in this neuron, what do you want to know? You want to know how much did this neuron contribute to your total loss. Then only you can adjust the values of parameters on this neuron. For this, what do? You backpropagate. When you are backpropagating, you multiply gradients at each layer. Now what happens is, by the point it reaches this layer, at each layer you are having a gradient value which is very small. Sometimes it may be very close to 0 as well. If you multiply that with the next one, that with the next one, and so on, by the time it reaches this neuron, this value will become insignificant. It will be so small that your value will be very insignificant, and hence there will be no updation done on this neuron. Like, it will be as good as not doing an updation. It will be something like 0.000, something like this. Then, even though you are doing that small updation, it won't make any sense. It will be almost as if you are not doing any updation to this neuron, which means your learning will become slower and slower. So your neuron, especially the initial layer neurons, at the end layers, the output layer and all, it will work. But when it comes to the initial layers, the back propagated value that reaches here will be very small because of this property of sigmoid. That is, it is always a very small value, and hence the final error, the contribution to the final error that you see from the neurons which are in the beginning points, beginning layers, those will be insignificant and your updations will be meaningless. And this is why you will see like your neural network stopped learning, because the gradient that is reaching here is almost 0, because of which you would have a feeling as if your neural network stopped learning. And this is the problem called as vanishing gradients. Your gradients are vanishing when you reach to the initial layers during backpropagation. So this is the main problem faced by sigmoid activation function. Let us see the next problem. This is also a very significant problem with this activation function. Let me erase these things off. If you Okay, so what is the second problem? Second problem, which is also a very significant problem. The second problem is that it is not zero centered. Zero centered. What is the speciality of zero centering? The speciality of being zero centered is, okay, I'll write here, not zero centered. Why should it be zero centered, and what is the problem when it is not zero centered? Let us understand this. First thing about sigmoid, you already know its value is between 0 and 1. From this itself, it is very evident that it cannot be zero centered because all values are more than 0, and hence the center can't be 0. Let us say instead its range is -1 to 1. Then you can say it is zero centered. Many times it would happen that some values will be on the left side, negative side, some will be on the positive side, and center will be 0. But in case of sigmoid, it can never be zero centered because all values are larger than 0. It is never taking negative values, because of which it surely is not zero centered. Next thing, what will happen if it is not zero centered? If it is not zero centered, gradients will always be of the same sign. I'm not saying gradients will always be positive. I'm saying all the gradient updations, they all will be of the same sign. And what is the problem with that? When all the gradients are of same sign, gradient updations will be biased. That is, all of them will be biased towards one side. And what will this lead to? When you are doing back propagation, you are actually trying to hit that minima. That is, for each neuron, you want to find out which is the best value, which is the value that minimizes the loss. So you want to hit this minima, but because your gradient updations are always very biased, because all are either positive or all are either negative, what happens? You won't be able to hit this minima. So instead of actually coming closer to this minima and trying to hit these updations will be biased, which will drive it in such a way that your updations will be zigzag. It won't be able to actually hit that optimal minima. This is the problem. So I just said this is the way. Let me show you why it can't hit. Otherwise, it's not fair, because I simply told you that, okay, it takes values between 0 and 1. So it can't take negative values. So gradients always have the same sign. So how can you believe this? This is where let us see mathematically why gradients have the same sign. Okay. Then it will be clear for you. Then it will be more logical instead of simply by hearting that all gradients have the same sign, right? You should not learn that way. You should understand what it is. So let us understand why gradients are having the same sign. We'll take an example. Let us say we'll take one particular neuron somewhere in the middle of a neural network. In that neuron, let us say your value that will come out, I'll call it Z. This will be sigma j. Let us say it is this value, wjxj plus b. Well, this b is the bias, and this wj, these are the weights that are there. Okay, and xj is the input, right? Then if I have an activation function which is sigmoid activation, then my activated neuron will be sigmoid of z. This will be the scenario. So this is the weighted output that is coming from the neuron, and this is the final output after activation function. Okay, so first you will have this output. This will be put into activation function in order to get final output from the activation function. Let us say your loss is L. This is your loss. Then how are you going to find the gradient for a specific weight Wj or Wi, let us say? How are you going to find the derivative of this loss with respect to that particular weight? Why should you find that? Only if you find the derivative of loss with respect to, let us say, some particular weight Wi, then only you will know how much should you update this Wi. That is dependent on the derivative of loss with respect to that particular weight. Then only you know how should you update that weight. What is the whole point of training? In training, you are trying to find out the right values of weight. So how do you find you are updating in each iteration. When you are updating during each iteration of training, you want to know how much to update, and that is decided by this gradient, right? Let us see what happens when you find this gradient. Instead of directly finding del L by del Wi, what you can do is you can take del L by del A. This will make it easier, okay? Into del A by, what is this A? It is activated value, okay? Del A by del Z. So Z is this. And then you can take derivative of del Z with respect to Wi, del Wi. This is how you can find out del L by del Wi. Okay. Next thing is, let us understand how each of these terms changes, what values they can take. First of all, we'll consider the easiest one, that is del A by del Z. That is this value. What is this value? You already know this. This is the derivative of sigmoid, because your activation is sigmoid. Derivative of sigmoid. How can you find derivative of sigmoid? Sigma dash of x, we learned this is sigma of x into 1 minus sigma of x. This is the derivative of sigmoid. So here your activation we named as A, which means this value will be A into 1 minus A. So this part is clear. And what do you think about this value? You know A is always a positive value. Sigma of x, this is always positive because it takes value between 0 and 1. What about that into 1 minus that value? This is also positive. This is also positive, which means this value is always positive. This is always positive. Del A by del Z, this is always a positive value irrespective of whatever be the scenario. Next thing. Let us understand the next term and how it is changing. Next term that is of importance here is, let us take this one, del Z by del Wi. If you take del Z by del Wi, what happens with this term? With this term, first thing you want to understand what will be the value of this. If you see Z, that is having this value, sigma over all the j, wj xj plus b. If you take derivative with respect to one particular w, what will remain? Only the corresponding x term will remain. That is, whichever is the xi corresponding to that particular wi, only that will remain, because all others will be cancelled out because you are taking derivative with respect to one particular wi. So, if you take derivative of this z with respect to one particular wi, what remains? Only the corresponding coefficient, not coefficient, the input value xi. So xi remains. If you take del z by del wi, only term that will remain will be xi. What is the value of this particular xi? Is it positive or negative? It can be positive, it can be negative, both are possible. But the point here is, whatever is the input value that is coming, the same sign will be given, right? If the input is positive, then it is positive. If the input is negative, it is negative. So till now it is clear. Let us see the next term, del L by del A. If you take del L by del A, what will be the sign of this particular value? If you understand what is this is the derivative of loss with respect to the activation. Which means in a neural network, you have loss, you are back propagating loss. Here is your neuron. Then the derivative of loss with respect to the activation here, this is your activation, that will be the error signal that is flowing back from the next layer. That is, whichever is this layer. From here, whatever is the error signal flowing back, that will be the derivative of loss with respect to your activation. So this actually indicates whether the output should have been higher or lower to reduce loss. So what are you trying to do? You are trying to reduce this loss. So when you are taking derivative of the error that is flowing backwards, from that you will get this information of whether the output from this neuron that is going forward, whether that should have been higher or if it should have been lower, in order to reduce this final loss. This is the information provided there, which means This value can also be positive or negative. Both are possible. But there is a catch here. You understood this is always positive. This is sometimes positive, sometimes negative. This is also sometimes positive, sometimes negative. Now you would think it can take either positive or negative. Then why did I say that initially? Why did I say that gradients will always take the same sign when you are using sigmoid? Why did I say that? Because from this analysis, it doesn't make much sense, because it feels like it can take either positive value or negative value. Then how does it make sense to say that always gradient will be of the same sign? This is what I am going to tell you now. This part is very important. Okay, you already know these three factors are there. Now for analysis, I'll write this part again. Del L by del Wi. This I had written as del L by del A into del A by del Z into del Z by del Wi. And how did I write these terms? This term I told it is xi. This term I told you it is a into 1 minus a. And you also know this is always positive. This can be positive or negative. This can also be positive or negative. So the point here is, if you take one particular neuron and try to understand, for that particular neuron, this part will always be constant. Why will it be constant? The reason is, all the weight updates for this neuron, let us say some particular neuron that is here, for this neuron, all the weight updates will be same sign as the corresponding xi. This is what I am going to prove. That is, whatever is the value of xi, the same sign of that will be all the weight updates in this case. The reason is, this part is actually flowing from here. So whatever is flowing backwards from here, that value will be same in case of all these. So when you take each of the i's here, depending on the xi, the value will be positive or negative, but it won't depend on this part here, because this part is flowing backwards from here. This thing, you know, it is always positive. This thing, that is the first part, this we understood it is flowing backwards from here. It is the same value that will flow backwards always. So because of that, this thing is constant. You can consider it as the same thing in all the updates of wi's. Then this, you know, is always positive, which would mean all the updations will be based on xi. And what about xi? Xi can always take the same sign. So whatever be the sign of xi, the same will be sign of all the gradients. What happens then? This forces optimization path to take a biased path. So how is it biased? Because you want to update weights. When you are updating your weights, all your gradients are taking the same sign as that of xi, which means all gradient updates will be biased towards one same side. And what does this do? You are trying to hit a minima. When you are trying to hit a minima and you are having a biased gradient update, you won't be actually able to come and hit this minima. Instead, it will move in a zigzag fashion. This is the problem. Because of this, you would find it very difficult to actually hit this minima. This is the problem when you are having in an activation function which is not zero centered. Because it is not zero centered, activation function always takes positive values, because of which activation function is always positive, because of which your gradient updation for any particular weight which is dependent on the derivative of loss with respect to that particular weight, it will always take same sign as that of the input. Same sign means it is possible that it is always taking same sign as that of xi, because this part is constant for all the i's. The del L by del A part, that is flowing backwards. A into 1 minus A part, that is always positive. You know, you are using sigmoid, so this is always positive. Because of which xi sign solely depends the sign of this, which means all those can take the same updation. Same updation means same direction of updation. Okay, so when the direction of updation is same, it becomes biased. If it is not same, what happens? Some gradients will cancel out with some other gradients which are positive and negative. This would mean it is not biased. That is the case when you actually manages to hit the minima. So that is what you actually want from an activation function. Okay, so this is why being not zero centered is affecting your learning process. Okay, so this is about not being zero centered. Next thing is these two are the major problems. Okay, first problem is that it is having vanishing gradient problems. That's what we initially learned. Second problem is that it is not zero centered. After this, you can also say another issue with this activation function is saturation for larger inputs. We already understood this point, that is whenever inputs are larger, it saturates towards 1 and your gradient will go very close to 0. So this is saturation for larger input. When I say larger, positive larger input or larger negative input, both are the same case. In both cases, sigmoid takes extreme values, that is either 1 or 0. Whichever be the case, derivative of sigmoid takes almost 0. This is the problem. So that means your larger inputs get saturated. There will be no updations on the neurons for such larger inputs because gradient becomes 0. Okay. And one more problem that you can say is that it is computationally expensive. So if you ask me whether 1 by 1 plus e power minus x, is it very expensive? You will understand that when we learn about other activation functions, something like ReLU and all, you will understand this is a costly operation. Okay, so as of now it may not seem computationally very expensive, and for the modern computers anyway, this is not a very expensive operation or something, but compared to other activation functions, something like ReLU or something, then this is a computationally expensive operation. Okay, and before we conclude, one more point I have to make here, that is you are having a lot of layers in your neural network. If you are using activation function as sigmoid, one more problem you can have is all these activations will take some value because sigmoid is between 0 and 1. It is not going to take 0 and get cancelled out. It may take very small values, something like 0.0001, but still this is a value and that neuron stays activated. So because all neurons take non-zero value in your neural network, all the neurons will be activated and there is some work that is to be done on each neuron in each pass. So this is also a negative for sigmoid, because when we learn about other activation functions which will sometimes take it to 0, you will understand why this is a computationally expensive problem. Okay, so which are the problems that we have seen? We have seen that one problem is about vanishing gradients problem. Then we saw it is not zero centered. This is the second problem. Third one is that it saturates for larger outputs. Third, we had seen it is a bit computationally expensive. Plus, we had seen that neurons will be always dense. Dense means all neurons will be activated. It won't take 0 value. Hence, they will be dense. So, these are the problems with sigmoid activation function. Mainly you have to see these two problems. Okay, one is vanishing gradients, other is not zero centered. Because of these problems, sigmoid is generally not preferred as activation function, especially in your hidden layers. Okay, in between the hidden layers, you generally don't take sigmoid as activation function.